In this module, we'll introduce the concept of no arbitrage and work through a very simple example of the application of the no arbitrage principle to pricing. Consider a contract that pays CK dollars at time t equal to k, where k takes values 1, 2, 3 up to capital T. And let's say that one has to pay a price P at time t equal to 0 in order to receive this contract, in order to get this cash flow. So the story is, here's time t equal to 0, where you pay a price P, here's time t is equal to 1, and all the way up to time t equal to capital T, and you get cash flows C1, C2, and so on up to C capital T. And the goal of this module is to introduce ideas of no arbitrage that allow us to fix this price P. It'll turn out that in certain circumstances we would be able to fix this price exactly, and in certain other circumstances we can only be able to bound the price. We can tell you the price cannot be larger than a certain quantity and cannot be smaller than a certain quantity. There are two ideas of arbitrage that are used in financial engineering. One idea is called weak no arbitrage, and the second idea is called strong no arbitrage. Both of these ideas essentially eliminate the possibility of a free lunch. Let's first consider weak no arbitrage. What this condition says is, suppose there is a contract such that the cash flows associated with this contract are non-negative for all times k greater than or equal to 1. C1, C2, C3, and so on up through C capital T are all greater than or equal to 0. If there is such a contract, then the price for this contract must be greater than or equal to 0. The strong no arbitrage condition says that suppose there is a contract for which the cash flows are non-negative for all times in the future, and there exists some time CL in the future such that the cash flow is strictly positive, then the price for such a contract must be strictly positive. Both of these conditions are motivated by the fact that in a market, if there are contracts for which you get something for nothing, then just by supply and demand, that contract will be priced to a point where you'll have to pay a fair price. Let's walk through the rationale for the weak no arbitrage condition. Suppose there exists a contract for which CK is greater than or equal to 0. That means you get non-negative cash flows for all times in the future, but the price for such a contract is less than 0. So weak no arbitrage says the price must be greater than or equal to 0. Here I'm assuming that the price is less than 0, and let's see what happens. Since CK is greater than or equal to 0, you do not owe anything in the future, and the buyer of such a contract receives minus P, because P is less than 0, which means you have to pay a negative amount to receive it, which is the same thing as saying you receive a positive amount at time t equal to 0. The buyer never loses any, and at the same time gets money at time t equal to 0. This is a free lunch. Weak no arbitrage condition says this cannot happen. Why can't this happen? This cannot happen because if there is such a contract, such that P is less than 0, then the seller of such a contract will start increasing the price. It's a bad deal for the seller. The seller will keep increasing the price. But for any price P less than 0, this is a very good deal for the buyer. So the buyers are still going to be there. And this price, the seller would keep increasing the price until P hits equal to 0. At least. She might be able to increase the price to be something greater than 0, but the weak no arbitrage condition doesn't allow us to figure out how exactly this price is going to work once the price becomes greater than 0. We can only say, using the weak no arbitrage condition, that the price will be increased until P becomes greater than or equal to 0. You can make the same argument from the buyer's perspective. Since it is a good deal for any price less than 0, the buyers will be willing to pay a higher price in order to compete. They will compete with each other until the speed less than 0 cannot be sustained in the market. Recall, in the other module, I talked about the fact that how prices get set by supply and demand. You again see here that the rationale for weak no arbitrage is built on supply and demand. We are building it on the fact that there are many buyers, many sellers. We are also using the fact that the information about the details of the contract are publicly available, are uniformly available to buyers and sellers. This is going to be important, and we'll emphasize this again on the next slide. Here, I'm going to work through the rationale for a strong no arbitrage condition. Suppose P is less than or equal to 0. Strong no arbitrage condition says that P must be strictly greater than 0 for a contract for which the future cash flows are greater than or equal to 0, and there exists some time where the cash flow is strictly positive. Since CL is greater than 0 for some L greater than or equal to 1, even if P is equal to 0, this is a free lunch. It's a free lunch as long as P is less than or equal to 0. Again, using the same arguments that we used before, the seller of such a contract will have an incentive to increase the price. The buyers will still be around because it's still a good deal at something positive. We cannot guarantee what the precise value of the price is going to be, but for some price strictly positive, it will still remain a good deal because there exists a cash flow CL which is strictly positive for some time L in the future. And again, buyers and sellers will compete in order to set the price P. The implicit assumptions that are underlying the no arbitrage conditions are the markets are liquid, which means there are sufficient number of buyers and sellers. If the markets are illiquid, the no arbitrage condition is not valid, and the bounds that we generate using the no arbitrage argument will no longer be valid. We also assume that price information is available to all buyers and sellers. The price information here basically means what are the cash flows. If there are buyers and sellers which are ignorant about the cash flows, then the price formation process will not happen. We also assume that the competition in supply and demand will correct any deviation from the no arbitrage prices. And this again presupposes that there is a market, these markets are liquid, the price information goes to every buyer and every seller so that they can decide how to set the price efficiently. In the rest of this module, I'll just walk you through a very simple example on how to use no arbitrage condition to price a very simple fixed income instrument. In the later modules, we'll go over more complicated examples where you use no arbitrage condition to set prices for more complex derivatives. So consider a very simple bond. What this bond gives you is $8 in 1 year, and we want to set the price for this bond. Suppose in the market, one is able to borrow and lend unlimited amounts at an interest rate R per year. So the bond pays $8 in 1 year. We can borrow and lend unlimited amounts at the interest rate of R per year. And we want to figure out what is a fair price or an arbitrage-free price for a contract that pays $8 in 1 year. We'll do it by constructing two different portfolios. So let's construct the following portfolio. You buy the contract at price P, and you borrow A divided by 1 plus R dollars at an interest rate of R. Consider the cash flows associated with this portfolio. In the future, in 1 year, the contract will pay $8, and you've borrowed A divided by 1 plus R at the interest rate of R, so you have to pay $8. These two cancel each other, so the cash flow in 1 year is A minus A equal to 0, so C1 is equal to 0. And what is the price of this portfolio? The price of this portfolio is P, the amount that you had to pay to get the contract, minus A divided by 1 plus R, because this was the cash flow that you received at time t equal to 0. So the net price that you paid for the portfolio is P minus A over 1 plus R. Now let's use the weak no arbitrage condition. The weak no arbitrage condition says that if the cash flows in the future, and in this particular case there is only one time in which there is a cash flow in the future, in 1 year, if the cash flows in the future are greater than or equal to 0, then the price must be greater than or equal to 0. C1 greater than or equal to 0 implies that the price of the portfolio Z must be greater than or equal to 0. Price Z is equal to P minus A divided by 1 plus R. This must be greater than or equal to 0, which means that P must be greater than or equal to A divided by 1 plus R. So we now get a lower bound for the price. No arbitrage, weak no arbitrage condition gives me a lower bound on the price And we got this lower bound by constructing an appropriate portfolio. Now, in the next slide, we'll get an upper bound for the price by constructing a different portfolio. So construct a portfolio, we sell the contract at price P and lend A divided by 1 plus R at the interest rate R. Now what happens? The cash flow is again 0 in the future because you've lent an amount A divided by 1 plus R at interest rate R. So in 1 year, this returns you a value A. Since you have sold the contract, you're now responsible to pay A dollars to the buyer of the contract in 1 year. These two cash flows cancel each other, and therefore C1 again is greater than or equal to 0. In fact, C1 is equal to 0, which is the same thing as greater than or equal to 0. It satisfies the condition that C1 is greater than or equal to 0. What about the price of this portfolio? The price of the portfolio is how much did you have to pay in order to construct this portfolio. Since you sold the contract at price P, you receive that amount. So that's minus P. Because you had to lend A divided by 1 plus R at the interest rate R, this is the outflow. So A divided by 1 plus R is the total amount that you had to pay. The difference between these two, A divided by 1 plus R minus P, tells you the price of the portfolio. The weak no-arbitrage condition tells me that since C1 is greater than or equal to 0, the price that I paid for this contract must also be greater than or equal to 0. So Z is equal to A divided by 1 plus R minus P. This must be greater than or equal to 0, which means that A divided by 1 plus R must be greater than or equal to P. If you combine this upper bound with the lower bound that we constructed in the slide just before, you get that P must be exactly equal to 1 plus R. Should this be a surprise? Not at all. All we are doing is constructing the net present value calculation using a no arbitrage condition. The advantage of doing this net present value calculation using the no arbitrage condition is that it clearly shows what are the assumptions that are needed in order for the net present value to exist. It relied heavily on the ability to borrow and lend at the interest rate R an unlimited amount. If these assumptions are not true, then the net present value is not the correct price, and we would have to use some other techniques to figure out what the correct price would be. The no arbitrage conditions would still be valid, except that we would have to use them with different portfolios perhaps. So what happens if the borrowing and the lending rates are different? I can't use net present value, but I can use no arbitrage. What if the borrowing and lending markets are elastic, which means that if you want to borrow or lend, the interest rate that you're going to be charged depends on the amount that you're borrowing or lending. What happens in that case? Again, the net present value calculation is not valid, but we can construct no arbitrage conditions which would give us, if not the exact price, at least bounds on what such a contract can cost.